3 days ago, a team of astronomers published a paper in one of the most respected scientific journals on Earth. And the discovery they described is so strange, so fundamentally disruptive to everything we thought we understood about the early universe that the scientists themselves are quietly hoping they got something wrong. Not because they want to fail, not because they do not trust their instruments, but because if they are right, an object exists in the early universe that should not exist. An object that looks like a star, but shines 100 billion times brighter than any star ever could. An object that is simultaneously a black hole and something that resembles a star at the same time. An object that our entire framework for understanding how the universe formed simply has no good explanation for. And this is just the latest in a long series of discoveries from the James Webb Space Telescope that have left the world's best astrophysicists in a state of quiet, controlled panic. Today, we are going to go deep into one of the most fascinating and genuinely unsettling scientific stories of the decade, because James Webb is not just finding new things in the universe, it is finding things that tell us our map of the universe might be fundamentally wrong. And the scientists studying these discoveries are experiencing something that is both thrilling and deeply uncomfortable. The feeling that you have opened a door and found something behind it that does not match anything in any of your textbooks. Let's start from the beginning. Because to understand why what James Webb found is so disturbing, you need to understand what scientists expected to find. And more importantly, you need to understand how dramatically reality differed from those expectations. The standard model of cosmology, which scientists call lambda CDM, is one of the most thoroughly tested and carefully constructed scientific theories in human history. It describes how the universe began with the Big Bang, how matter clumped together under gravity to form stars and galaxies, how dark matter provided the scaffolding for large-scale structure, and how the expansion of the universe is being accelerated by a mysterious force called dark energy. This model is supported by an enormous body of observations. It correctly predicted the distribution of galaxies across the sky. It correctly described the cosmic microwave background radiation, the faint glow of heat left over from the Big Bang that permeates all of space. It successfully modeled the formation of the first stars. For decades, the scientific community's confidence in lambda CDM has been extraordinarily high, and rightly so. But every model has assumptions. And one of the core assumptions of lambda CDM is that the very early universe was relatively simple. In the first billion years after the Big Bang, there had not been enough time for extremely massive structures to form. The first stars were just igniting. The first galaxies were just beginning to coalesce from clouds of primordial gas. The first black holes were just beginning to grow from the seeds left by dying stars. This is not a guess. This follows from the mathematics of how gravity works and how quickly things can accumulate mass when starting from a nearly uniform distribution of gas. The early universe, according to our best models, should look like a cosmic nursery, young, simple, diffuse, and not yet organized into the massive structures we see today. James Webb showed up and looked at that cosmic nursery, and what it found there looked nothing like what the models said should be there. Not slightly different, not subtly off. Completely, inexplicably, jaw-droppingly different in ways that made some of the world's best cosmologists stop and ask whether they had gotten something fundamentally wrong. That is the context for everything that follows. Remember that context, because it makes every subsequent discovery more significant. When the James Webb Space Telescope launched on Christmas Day 2021, the world celebrated. For 30 years, astronomers had been dreaming of this instrument. It was delayed, over budget, plagued with engineering challenges. But when it finally opened its golden mirror to the sky and began sending back data in the summer of 2022, the images were breathtaking. Deep field images showing thousands of galaxies in a patch of sky, no bigger than a grain of sand held at arm's length. The telescope was performing beyond its own design specifications. Scientists were ecstatic. And then the surprises started arriving, and not the pleasant kind. The first data from Webb's deep field images showed something that immediately triggered alarms across the astrophysics community. Scattered throughout the images, appearing in almost every deep pointing of the telescope's infrared camera, were hundreds of tiny, faint, bright red objects. Objects that nobody had ever seen before because no telescope before Webb had been powerful enough to see them. Astronomers named them little red dots. And within months of their discovery, some of the most respected scientists in the field were using a phrase that sounds dramatic but was being used sincerely. They said Webb had broken cosmology. Here's why. To understand what a little red dot is and why it caused such alarm, you need to understand a basic fact about the universe. The universe has a history. It started with the Big Bang roughly 13.8 billion years ago. In the very early universe, there was nothing but hydrogen gas and helium slowly coming together under gravity to form the first stars and eventually the first galaxies. The process takes time, enormous amounts of time. Under the standard model of cosmology, which is the best mathematical framework we have for describing how the universe evolved, very massive, very complex structures simply cannot exist in the very early universe. There has not been enough time for them to form. The little red dots appeared to violate this principle in a dramatic way. They were appearing in the early universe, roughly 600 million to 1.6 billion years after the Big Bang, and when astronomers analyzed their brightness and spectra, the initial calculations suggested these objects contained black holes that were unimaginably massive. Black holes that were millions or even hundreds of millions of times the mass of our sun packed into the very first billion years of cosmic history. Black holes that, under every model we had for how black holes grow, simply could not have had enough time to become that massive that quickly. It was like finding a fully grown oak tree in a pot that was only planted 2 weeks ago. The tree cannot be that old, but there it is. By summer of 2023, dozens of discovery papers had been written about the little red dots. Scientists had identified 3 traits that all of them shared. They were tiny in apparent size. They had an unusual V-shaped spectrum, meaning they were bright in ultraviolet light and bright in optical light with a dip in the middle. And they showed broad emission lines from high-velocity hydrogen gas, the kind of signal you normally associate with an active black hole consuming material at a furious rate. A few appeared in every single deep field pointing of Webb's camera. They accounted for a few percent of all known galaxies in the first billion years of cosmic time. There were hundreds of them, and none of them had ever been seen before, by any telescope, ever. The cosmological implications were staggering. One widely cited paper by researcher Boylan Colchin in 2023 argued that if the mass estimates for these objects were correct, the abundance and mass of the black holes implied by the little red dots was completely incompatible with the lambda CDM standard cosmological model. Lambda CDM is the standard model of cosmology. It is the framework that describes dark matter, dark energy, the large-scale structure of the universe, and how everything evolved from the Big Bang to today. It is supported by decades of observations and represents the best scientific understanding of how the universe works. And some researchers were saying that these tiny red specks in Webb images might be incompatible with it. That is what scientists mean when they say Webb might have broken cosmology. Not that the universe broke, but that our model of the universe, the mathematical description that has been our guide for decades, might be missing something fundamental. Now here's where the story becomes even more layered and strange. Because the scientific community did not simply accept the panic, they pushed back, they did what good science demands, they questioned the assumptions, they looked for errors. And this is exactly why the title of today's video is what it is. Scientists hoped these discoveries were mistakes, not because they are incurious, but because if you have to choose between your instruments being slightly wrong and the entire cosmological model of the universe being fundamentally broken, you start by checking your instruments. And something remarkable happened. The more scientists dug into the little red dots, the weirder they got. But some of the initial alarm began to soften as errors were identified. In January of 2026, a study published in the journal Nature by a team led by Rusakov showed something important. The initial mass estimates for the black holes inside little red dots were almost certainly wrong, significantly wrong. The dense gas cocoons surrounding these objects were artificially broadening the spectral lines that astronomers use to measure how massive the central black hole is. The gas was essentially creating a false signal. When the researchers corrected for this effect, the implied black hole masses dropped by a factor of roughly 100 times smaller than previously thought. That is a significant correction. If the black holes inside little red dots are 100 times less massive than early measurements suggested, many of the most alarming cosmological implications go away. The objects become strange and fascinating rather than universe-breaking. The panic about broken cosmology was, in large part, a measurement error, and scientists who quietly hoped that was the case felt some relief. But relief in science is never total. Because even as the mass correction removed some of the alarm, it raised new questions. And then Webb kept looking. And what it found next is what brings us to the discovery published just 3 days ago that kicked off this entire video. On August 12, 2026, a team of researchers led by Rohan Naidu at MIT published a paper in Nature describing a single object that may be the most bizarre thing ever detected in the history of astronomy. They named it MOM BH1, after their survey called Mirage or Miracle. They call it a black hole star. And it is exactly as strange as that name sounds. The object was seen 660 million years after the Big Bang. To put that in perspective, the universe is 13.8 billion years old. Webb was looking at something that existed when the universe was less than 5% of its current age. And this object is radiating energy at a level 100 billion times brighter than any star in the universe could possibly produce. The laws of physics place a fundamental limit on how bright a star can be. It is called the Eddington limit, and it is determined by the balance between the radiation pressure pushing gas outward and gravity pulling it inward. No normal star can exceed that limit by a factor of 100 billion. It is physically impossible. So this is not a star, at least not in any conventional sense. What the MIT team found when they analyzed the spectrum of MOM-BH1 in extraordinary detail is something that challenges every existing category. The object appears to be a black hole, roughly 100,000 times the mass of the Sun, wrapped inside a vast cocoon of hydrogen gas approximately the size of our entire solar system. The black hole is consuming material so rapidly it is in what physicists call a super Eddington accretion state, meaning it is eating faster than the theoretical limit for how fast black holes are supposed to be able to eat. The gas cocoon around it makes it look, from a distance, almost like a star. It has a warm extended surface that glows. It has a spectrum that superficially resembles stellar emission. But the amount of energy it is producing is so enormous that no stellar process can explain it. The Balmer break in MOM-BH1's spectrum, a specific feature that astronomers use to characterize these objects, measured at a value of 7.7. That is stronger than any known population of stars can produce. There is no arrangement of stars, no age of stellar population, no combination of star types that can generate a Balmer break that strong. The only explanation that fits the data is that a black hole is the engine. The team is calling MOM-BH1 the first direct spectral evidence for super Eddington accretion inside a dense gas cocoon in the early universe, and they believe it may be the best explanation yet for what the little red dots actually are. Not the galaxy-breaking monsters of early estimates, but these strange hybrid objects, black holes wrapped in gas cocoons, radiating at impossible intensities, lurking by the hundreds in the very early universe. But here is where it gets even more extraordinary. Because a competing explanation arrived just 1 week before the Nature paper on August 5th, 2026, from researchers at the Harvard Center for Astrophysics. And their theory is, if anything, even more mind-bending. The Harvard team proposed that some little red dots are not black holes wrapped in gas. They are living stars, not ordinary stars. Not stars like our sun, stars roughly 100,000 times the mass of the Sun, pulsating violently, shedding nitrogen-rich gas shells in the final moments before they collapse, and create the universe's first supermassive black holes. These objects have a name. Scientists call them supermassive stars, or population 3 supermassive stars, referring to the very first generation of stars believed to have formed in the universe before any heavy elements existed. For decades, supermassive stars have been a theoretical prediction. The idea is that in the very early universe, before things were as chemically complex as they are today, gas clouds could collapse into monstrous stars of unimaginable size. Stars so massive they are inherently unstable, stars that cannot live long, but stars that, in their brief, violent lives, might produce the seeds of the supermassive black holes that sit at the centers of almost every large galaxy today, including our own Milky Way. Nobody had ever actually seen one until maybe now. The Harvard team's model does something that the black hole model struggles to explain. It accounts for a strange chemical signature that keeps appearing in the little red dots, an anomalously high ratio of nitrogen relative to oxygen, far higher than any normal stellar or black hole process should produce. The supermassive star model can explain that nitrogen anomaly through the unusual nuclear burning processes that occur inside stars of that extreme mass. It also explains the V-shaped spectra and the compact appearance. If this interpretation is correct, according to the scientists at Harvard's Center for Astrophysics, we are not just seeing black holes consuming gas in the early universe. We are watching the very moment that some of the universe's first supermassive black holes are being born. We are watching stars that are 100,000 times more massive than the Sun in their final, brilliant, violent death throes. The researchers put it directly in their press release. If our interpretation is right, they said, we are not just guessing that heavy black hole seeds must have existed. We are watching it happen. The decisive question now is which explanation, or which combination of explanations, is correct. The two models, the black hole star and the dying supermassive star, may not even be mutually exclusive. They could apply to different objects within the broader little red dot population. Webb is already being pointed at more of these objects to gather the higher resolution spectral data needed to distinguish between the models. Both teams have named that as their next target. The answer may arrive within months. But take a step back from the specific scientific debate and appreciate what is actually happening here. We built a telescope powerful enough to see the very first billion years of cosmic history. We pointed it at the deep universe, and it immediately showed us objects that nobody predicted, nobody expected, and nobody had a ready explanation for. Objects that made some scientists fear our model of the entire universe was wrong. Objects that turned out to be real and strange in ways that are still not fully resolved years after their discovery. Objects that may be the birth moment of supermassive black holes, watched in real time across 13 billion years of cosmic distance. This is what the James Webb Space Telescope was built to do, not to confirm what we already know, to show us what we do not know, to push our understanding to its edges and then past those edges. Every time Webb causes a scientist to say, "I hope this is a mistake," it is actually doing its job perfectly, because the discoveries that matter most in science are always the ones that don't fit, the ones that refuse to be explained by existing frameworks, the ones that force us to build better frameworks. And the story of the little red dots is not over. In a July 2026 study, researcher Pierluigi Rinaldi showed that the host galaxies of little red dots, the actual larger galaxies surrounding these bright central objects, simply vanish below Webb's detection threshold at high cosmic distances. An entire galaxy can disappear from view, leaving only the blazing, bright central dot visible. That means for years, astronomers were trying to understand these objects without being able to see their full context. They were like trying to understand a city by looking only at its brightest streetlight. Now that we understand the detection limitations, the picture is becoming clearer. But clearer does not mean simple. It means more detailed, more nuanced, and in many ways more surprising. The James Webb Space Telescope has been operational for 4 years. In that time, it has seen possible direct collapse black holes that may have formed by the collapse of entire gas clouds rather than dying stars. It has detected galaxies that existed only 280 million years after the Big Bang, before the universe was even 2% of its current age. It has seen a galaxy that does not spin, which should not be possible for a young galaxy that formed within the first 2 billion years after the Big Bang, because young galaxies are supposed to still be actively accreting rotating material. It watched a gamma-ray burst that lasted 7 hours, when gamma-ray bursts normally fade in under a minute. It found exoplanets with atmospheres that defy every model of planetary formation. It discovered a new moon orbiting Uranus, so small that nothing before Webb could have detected it. And now it has found what might be the first black hole stars ever directly observed by any instrument in human history. The pattern running through all of these discoveries is important. It is not that Webb is finding things that are slightly outside the predictions of our models. It is finding things that are dramatically, sometimes incomprehensibly, outside those predictions. And the scientific community's response to each discovery follows a very consistent arc. First, disbelief, then a rush to find the measurement error. Then, when no error is found, a slow and sometimes reluctant acceptance that the universe contains something new. Then a scramble to build new theories that can accommodate the new data. Then, those new theories generate new predictions. Then Webb tests those predictions. And sometimes the new theories hold. And sometimes Webb shows us something that breaks them too. This is science working exactly as it should. The telescope is not a confirmation machine, it is an exploration machine. Its job is not to validate what we already know, its job is to push into the unknown and report back. And every time it reports back with something that does not fit, that is not a failure. That is the highest possible success. That is the moment when human knowledge advances. Every one of these discoveries made scientists uncomfortable. Every one of them prompted at least some researchers to quietly hope the data was wrong. And every one of them turned out to be real, strange, fascinating, incompletely understood, but real. That is what is happening at the edge of human knowledge right now. The most powerful telescope ever built is sending back images from the beginning of time itself. And those images keep showing us things that challenge us to think deeper, to measure more carefully, to be humble about how much we thought we understood, and to be excited about how much remains to be discovered. And here is perhaps the most profound part of this story. The James Webb Space Telescope is not near the end of its observations. It has enough fuel to operate for potentially 20 or more years. It has barely scratched the surface of the sky. It has looked at deep fields covering tiny fractions of the total sky, and already found hundreds of objects that break or strain our models. What happens when it looks at more sky? What happens when it stares longer at regions it has already surveyed, gathering more photons, detecting fainter and more distant objects? What happens when the next generation of ground-based, extremely large telescopes comes online and follows up on Webb's discoveries with even more detailed spectroscopy? The answer, if the pattern of the last 4 years is any guide, is that we will find more things that do not fit, more cosmic mysteries, more objects that make scientists reach for their keyboards to write a paper titled, "We hope this is a measurement error." And most of the time, it will not be a measurement error. It will be the universe, vast and ancient and indifferent to human theory, showing us one more example of how much stranger it is than anything we imagined. The little red dots taught us that the early universe is crowded with objects we did not predict. Mombi H1 taught us that black holes in the dawn of cosmic time can grow to extraordinary sizes in ways that push against the boundaries of known physics. The supermassive star hypothesis taught us that the very first stars in the universe may have been monsters so large they beggar description, and they may have been the seeds from which every supermassive black hole, including the one at the center of our own galaxy, ultimately grew. The universe is stranger than we imagined. James Webb is proving it one red dot at a time. If this story lit something up in you, share it with someone who needs to hear it. Because this is happening right now, this week, this month. The papers are being published right now. The debates are being had right now. Scientists around the world are staring at data from the edge of the observable universe and asking questions that have no answers yet. Questions that may reshape our understanding of how everything began. The universe is revealing itself in ways nobody has ever seen before, in ways no previous generation of humans even had the tools to witness. And you are alive at exactly the right moment to watch it happen. Do not look away. The next discovery might be the most important one yet, and it could arrive any day now.